this type of site. Just
Hi everyone.
page and you scroll.
Can we please quiet down a bit? Thank you all for coming. If you'd like to sign up to our email list or if you'd like to present, please scan these 2 QR codes. And I encourage everyone, please take a minute to scan the attendance QR code just to confirm that you were actually here. So today, Julia's going to be presenting a paper on astroscience called Unveiling KT Eridani, a possible nova super remnant revealed by the Condor Array Telescope.
Okay, so hi everyone. I'm going to be presenting on an article written by Dr. Shara and his colleagues, and I'm doing a research project with him. And so the title is Introducing the Condor Array Telescope, a possible nova super remnant surrounding the putative recurrent nova KT Eridani. So before we begin, I want to highlight some key vocabulary to understand with this article. So recurrent nova, read as RN in the article, are binary star systems, which are two stars that orbit a constant center of mass. And this binary star system is where a white dwarf, which is a dense compact core of a dead star, that repeatedly steals matter from its companion star. This process typically occurs from every decade to a century. And then a supernova versus a nova. They seem similar, but a supernova is a bright explosion of a white dwarf star, causing the death of a star. Meanwhile, the nova is a smaller, less bright explosion on a white dwarf star. So that would be a nova, not a supernova. And then a supernova remnant is the expanding shell of gas and dust that an exploding star leaves behind in a supernova explosion. Okay, so this novel is about KT Eridani, which is read as KT Eri in the article, and it's a recurrent nova in the constellation Eridanus that had an explosion in 2009. So that's the constellation. And then SALT spectra is the analysis of light emitted or absorbed by celestial objects, and it stands for the South American Large Telescope. And then thermonuclear runaways occur when a white dwarf accretes material from a companion star and explodes on the surface of the star. And it's a chain reaction nuclear fusion, which is where light nuclei get heavier. So next we have to understand what is the Condor telescope. So Condor is the name of the telescope that was built in 2021, and it consists of 6 small aperture high quality refractors on a shared mount. So that would be these. And then it is also an ultra sensitive wide field and low scatter design, which means the images it captures are high quality and it has limited noise, and it can capture images from extremely far distances. So my current project with Dr. Shara is image validation, which means I look at the images the Condor telescope takes and check them to ensure acoustic quality amongst all of them. Oh, and Condor is located in New Mexico, and that is what New Mexico looks like at night. So how do nova become recurrent nova? This slide basically just explains the difference between nova and recurrent nova. What you should take away from this is that recurrent nova explode frequently, while nova just explodes once. The critical mass is the smallest mass the star can be before it explodes. And the higher surface gravities that recurrent nova have call it the critical mass, which makes it explode more often. So Condor has 6 filters, which are basically just 6 different lenses that it takes based on one photo. So it uses these narrowband filters to isolate specific elements that contain specific wavelengths of light. So the first one detects ionized helium, which can indicate regions with hot stars or energetic shocks. The second row is how doubly ionized oxygen is captured, which is a strong emission line that is commonly found in planetary nebula and supernova remnants. And then HE1 detects natural helium and provides insights into regions of lower energy ionization than HE2. And then H alpha, which is third from the bottom, captures hydrogen alpha emissions, which is the strongest spectral line produced by hydrogen gas. And then N2 detects ionized nitrogen, which is often found alongside hydrogen and ionized gas clouds. And then S2 captures ionized sulfur, which helps astronomers analyze the ionization state of gas clouds to rule out certain types of energetic events. And I realized that I did this. Okay, and then it's important to separate the images that Condor takes into these filters so that the background noise is reduced. And then basically you subtract the luminance image from the narrowband image and it isolates the specific emission from the gas being targeted. So this is all from one figure, and it shows the same image through the 6 different narrowband filters that I just explained. And what we're looking for in these images is the supernova remnant, which is the shell-like cloud of dust and gas that's left behind after the explosion. So does anyone have any guesses as to which of these 6 images is best showing the supernova remnant? Yeah?
The rightmost?
Yeah. So, basically before I explain that, the tick marks at the very point of these is like KT Eridani. The rest of it is just like other stars and like noise. So it's really small in this image. But yes, that's right. So the H alpha filter best shows the supernova remnant, which means that it is made of hydrogen. It is made primarily of hydrogen alpha gas. So you can see it's basically just like this very light thing that's around KT Eridani. Okay, so this figure on the left shows, these two show the same image that was shown before with the H alpha. And the orange X shows where KT Eridani was 51,000 years ago. And the magenta tick marks show the exact location of KT Eridani, like currently. And then the green arrow shows the projected movement of KT Eridani over 25,000 years. And this suggests the object is moving away from the central nebulosity, which could possibly imply the gas cloud is material ejected earlier. And then the right figure shows, if you see this vertical line has the yellow, blue, and red, and it's showing the difference between H alpha and N2, those two filters. And it has, so those colors are drawn here in this figure, and this is the same exact image as this. It's just the outline is drawn with those different colors, and that's KT Eridani right there. And as you can see, the red line has the lowest flux density. The flux density is what's being measured here with these different colors. So the red line has the lowest one because it surrounds like the entire shell, the supernova remnant, and it's the most dispersed. And then the cyan outline, it outlines the main body of KT Eridani and the supernova remnant. But as it's like more closely together than the red one. And then the yellow one has the strongest flux density difference, outlining the innermost brightest core of the ejected material. And you can see like it's darker towards the middle, and that's kind of what the yellow is covering. And that area is where the hydrogen-dominated gas is densest and emitting the most light. telescope graph. And the horizontal axis measures the wavelength in angstroms, and this covers the red part of the optical spectrum, and it focuses on the key emission lines. And then the vertical y-axis measures the spatial position along the slit in arc seconds from 0 to 400, and it represents the length of the slit projected on the sky, crossing the inner part of the Shell Nebula surrounding KT area. So, okay, so as you can see, the H alpha line is the broadest, and it's the most prominent feature in the nebula itself. So it's like broader on the night sky lines, and this broadening indicates the velocity dispersion in the shell's gas, consistent with expanding ejecta from the supernova remnant. And then there's no velocity gradient, so the H alpha line doesn't show a systematic shift or tilt across the slit, meaning no clear radial velocity change along this part of the shell. And then the so the Ni and Si lines, this is the Si, and then Ni1 is right there. And they're fainter, they're present, but they're fainter and narrower, so they're most likely just from the sky or diffuse interstellar medium. And then also, so these two lines are receiving control from the salt spectrum, etc. And then these lines that are indicated in pink are just background noise from the night sky. Okay, so to summarize this article basically introduces the Condor Array telescope and explains its capabilities, and it basically confirms the KT Eridani as being the second recurrent supernova remnant, and this would be only the second supernova remnant ever found, and the first in our galaxy. So, future direction. The subsequent studies have identified additional supernova remnants around recurrent nova, and these findings emphasize the need for systematic surveys in nearby galaxies. And basically, this shows the capabilities of the Condor telescope in identifying future supernova remnants. And then also, the Condor series has continued. So this is the 4th article in the Condor series, but they have a part 5 and a part 6 that basically just extend on what they've been doing with the telescope. So yeah, that's pretty much it. So I'd like to thank Dr. Shara from Museum of Natural History, and then my journal club group, which is Juliana, Aiden, Sarah, Mr. Maxwell, journal club. So yeah, thank you. Any questions? Yeah.
Why is it important to identify or to understand recurrent supernovas?
I mean, I think that, well, they're basically explaining that, like, you could, like, predict when the next star will, when the white dwarf will explode. So I think people, like, they just want to, like, be able to predict when it's going to explode. I'm not sure how it wouldn't really affect us here, but, like, these white dwarfs explode in our galaxy, so I think it's just, like, to be able to track them. But yeah.
Students, don't be shy. If you have something you don't understand, ask.
Yeah.
Why did the keep carrying on moving away from certain stars?
I think so. That's basically implying that it's I'm pretty sure that that's showing that it's like basically it's moving away from its central nebulosity, which means that it's basically ejecting its material, and that shows that it's like that's basically one of the guidelines for recurrent nova, recurrent supernova. Yeah, that's basically it. I'm pretty sure.
Is H alpha in like every supernova or just this?
Yeah, I'm pretty sure it is. The H alpha, so that's like the filter that the telescope used. And the fact that when the telescope captured that image under that filter, that it showed the best, like that it showed the supernova shell the best. I think that's also one of the guidelines for a supernova remnant, like having that hydrogen alpha like shell, because that like if it has a shell, that's basically implying that it was like in an explosion. Oh yeah.
So there's another type of objects that's called quasars that also emits like radiations like every like they have periodically. So just curious, how do we distinguish the recurring novas from those quasars?
Wait, sorry, I can't hear
So
you.
there's another type of like astronomical object that also radiates like lights like
Yeah.
the periodic manner called quasars. So I'm just curious, how do you tell from your data that this is not quasar, it's a supernova?
I think that they based this data off of, so there was a first supernova remnant discovered in the Andromeda galaxy, and they based that, so what the restraints were from that data, they kind of based that off of how to determine that Eridani was its own supernova remnant, like recurrent supernova. Yeah, it's based on that data from a previous article, basically. Yeah, so the next article will be Eric Chen on Nobel Prize AI, the alpha-fold revolution in protein folding. So please come to that. That will be next Thursday at 8 a.m. here. So thank you.